So let's now take a look at how to really implement a parser. So one of the first approaches to building parsers is what we describe here, the so-called recursive decent parsing. So let's take a look at an example for a simple grammar that is able to model control flow and loop statements in a hypothetical programming language, so if and while statements. So from our non-terminal symbol p, we can derive either a simple if statement, so if non-terminal symbol cont for condition, then non-terminal symbol some statement, and an end, which just encapsulates our statement here. Or if we want a complex if statement with an else, we can have if non-terminal symbol cont, then non-terminal symbol statement. Now we have an else and another statement non-terminal symbol and the end again. Or as the third production for p, we can have while non-terminal symbol cont again and then a do non-terminal symbol statement and an end. Now in order to type a bit less, we can shorten this, but it has the same meaning. So let's say we go from p to I, non-terminal symbol c, terminal symbol t for then, non-terminal symbol s for statement, and then the end we encode as z, just for saying we're finished. Or we can include the else. That's why we used the z before. We wanted to use the e for the else. So we have I, then condition, then t for the then a statement, then an e for the else, another statement, and a z for the end. Or we can have a while loop, while, c, condition, do, statement, and again a z for the end. And now we also resolve just our c's and s's here. So c just goes to a single character c, which stands for a condition, and s stands for a single input terminal character s, which stands for a statement. So this string here, ICT, SE, SZ, let's try to parse it. So what are we doing here? A top-down parser, as the name says, begins at our start symbol. Well, start symbol is p, so again, by convention, our first symbol is our start symbol, and then it chooses a production. So essentially, when we are at the start of our parser, we have seen in our grammar, okay, we need to somehow derive something from our non-terminal symbol p. So what can that be actually? Well, if we can only look ahead by one token and we read an I, we are able to choose between two productions here. So if we read an I as the first non-terminal symbol, so as the first token, those two productions obviously would be possible to choose. So either the one without the else or the one including the else. Now, we need to make a decision here because we don't want to have non-deterministic parsers. So we cannot make this choice before we see more of that token stream. So this is a grammar again that has a problem. And we've already seen how to solve this problem. We are solving this problem using our left factoring approach to make this problem decidable when we have only one character of lookahead. So left factoring, and you can try this out for yourself, generates the following grammar. So now we go from our non-terminal symbol p, our start symbol, either to just ICTS, so the common prefix for the simple if and this if including the else, and then a new production p prime, or we include our while loop as before, and p prime can now simply be our end, or it can include else and then a statement and then the end, and c and s are unchanged, so like before. So this resolves our problem of having some decision to take, some decision without having a long look ahead. So if we use this changed grammar now, this modified grammar, when we read an I at the beginning, well, we only have one production to choose, which is the first one here, because the other production starts with a W. So we're starting here. We know we have an I, so we can start building our parse tree now. So we can expand our non-terminal symbol p here to exactly this new syntactic form here. So we know we need a terminal symbol I, we've just read this one, and we know after this comes a non-terminal C. After this non-terminal C we have a terminal symbol T, then we have a statement, and then we can resolve the new non-terminal symbol P prime, which we've seen already is this production here. So let's continue going down, and that's why this is called recursive descent, our parse tree here. So what we're doing is we're taking this parse tree and we're extending it downward until we have resolved all of our non-terminal symbols. So recursive descent parsing implies that we follow the children of our current parse tree node that we consider down to the leaves. And the leaves, as we've seen in parse trees, always have to be terminal symbols. So we resolved P to this syntactic form here, so we have it here. So let's now see if we can parse ICT as E as Z. So we follow the tree from P to its first child, and on the right hand side now we've visualized the input token sequence. So at the beginning of our parser, the arrow here indicates the parser's position in the token stream. So we've just started and we figured out, oh, we need to start with P. So we can expand P to this sequence here, and now we can read the first input character and can see, oh yeah, hooray, it's an I. We have an I as look ahead, so we know it matches our first production for P here, but not our second one. So now we can cut this I off and know the remaining token stream here, so because we've already consumed this I, is now CTS ESZ. So let's continue parsing. So we've read the I in our input token sequence. Our next input character is a C. So we're at a leaf in our parse tree here. So what we do now is we need to backtrack to our P and go to our next symbol here. Our next symbol is a non-terminal C. A non-terminal cannot match any token. So we need to pick another production now here. So let's see what happens. Now, we need to figure out how to resolve our non-terminal symbol C, and we find out, oh, there's only one rule in our grammar to resolve this non-terminal symbol C, and this resolves to a terminal symbol, a lowercase c. By coincidence, obviously, our lookahead is also a lowercase c, so that's what we're reading now as lookahead as our next character. So what we can do now is we can pick this production here from non-terminal symbol C to terminal symbol C, and we can annotate this in our tree, so our tree grows downward here, and we have resolved the next one. We can remove the C from our token sequence here, from our input token sequence, and what remains is TSE as Z. Okay, now let's continue. So the next terminal symbol in P, so we're going upwards again and going down the next one here. The next terminal symbol is a T. Oh well, the lookahead is also a T. Hooray, we can consume that token here and expand the tree once more. So our remaining token stream is now SE as Z only. We've taken away the T. And we can go to the next step. So the next non-terminal in our production here is the S. So we know again, if we have a non-terminal symbol, we need to expand this further. So we need to check what can we expand an S to. So from S we can only derive a terminal symbol, lowercase s. So let's expand the tree again. Oh, by coincidence it matches. We have an S here. So we have expanded our tree, and we can remove this S again from the input token sequence. So we're left with E as Z. All right, and the next step here. So the final non-terminal in our first production here now is P prime. So now we have to resolve P prime here. So now we have two choices here. So P prime can either resolve to a Z or to the sequence E, non-terminal symbol S, and the Z at the end. So now we need to check what's going on. So our next input token in our sequence is an E. So if we look at our both possible productions for P prime, the first one would have a Z at the beginning, so that doesn't work. The second one has an E at the beginning. Hooray! So now we expand our tree downward again. We choose the second production for P prime. And we can use this by using only one single token of lookahead now, because we've done this left recursion elimination here. So we can resolve our P prime now to our sequence E, non-terminal S, and Z at the end. We can remove the E at the beginning because we've matched this right now, and our remaining token stream is S and Z. So the remaining steps are very similar to the ones we've already seen. We're just one level down the tree here. So we know the next one is a non-terminal symbol. We have to resolve this. We know we can only resolve a non-terminal S using that production here. So we end up as an S here, remove the S again, and finally we can match our Z here because that's the final terminal symbol in P prime. So we have Z here, and we can backtrack up again. We've successfully resolved this production down here. We've successfully resolved the upper level production down here. We can move back to P, and when we resolved all and find no further children, and we haven't found any error, so any step in which we couldn't apply any of the possible productions, we know we were able to match all of our characters, so we know the input matches our grammar, and so we can say, hooray, yes, we've successfully matched the input token sequence ICTSESZ to a grammar, and we've built some sort of derivation so we know how it fits and which rules were applied in sequence here. So this is why it's called recursive descent. So you go through all of this recursively here, and you go as deep as you can until you end up only having terminal symbols here at the leaves of your tree. And of course, all the nodes inside of your tree here are then non-terminal symbols again. So to summarize top-down parsing, we do some sort of predictive parsing by recursive descent. So what we do is we start from the start symbol here, which forms the top of our derivation tree. Then if we have a terminal symbol, we verify that the terminal symbol matches the input. And then we try to pick a unique production for non-terminals based on the look-ahead. So that's important why this ambiguities need to be removed from our grammars here. And then we can expand the syntax tree by the productions we can derive by picking this unique production before. And then recursively just treat the new subtree in exactly the same way. So that's why we have a recursive descent parser here. Now this requires that the grammar we give our parser is suitable for that. That we've seen, we can adapt them somewhat. We can apply left factoring if there is a common look-ahead that prevents us from picking the right production. We can eliminate left recursive productions. So we've only seen left factoring in our action so far. But now let's take a look at one other grammar. So essentially, this is a form of LL1 parsing already, because what we do is scan from left to right. We use the leftmost derivation. So from left to right, the scanning is the first L here. Leftmost derivation is the second L. And then in brackets here, our parameter, the 1, means we only need one symbol of look-ahead. And that's, of course, a very simple way of parsing. So let's look at another grammar. So now we want to try implementing a recursive descent parser in C code. And recursive descent parsers can be easily implemented by hand. If you're interested in a really complex example of how this works, I can recommend Niklaus Wirth's book on compiler construction. This is free to download from his homepage. It's a very short book, so it implements a complete compiler for a subset of, depending on the edition you get, of one of his programming languages he designed, so Pascal, Modular, or Oberon. And this whole book is like about 130 pages, and it includes all the source code to implement your compiler, including scanning, parsing, and code generation. Now, we won't discuss a 130-page book here completely now, but you learn all about things like these in the run of the semester. Let's first look at a very simple example. So let's say we have this grammar here. From our start symbol, non-terminal A, we can either derive terminal symbol A, non-terminal symbol A followed by a terminal symbol C, or just a terminal symbol B. So let's try to naively implement this parser. So the first thing we need to have is an interface to the scanner. Let's say we have a very simple interface to a scanner, which is a function called next. Next calls the scanner reads whatever is required and returns a symbol here. So in this case, it's simply single characters here. So we start reading the first symbol here. So we call next for the first time, which delivers us the first symbol in our input stream. And now we need to write code that chooses the production. So either the first one here or the second one here. And we do this by checking for the first character in each of these productions here. So if our symbol is character A, well, then we know we need to read another symbol here, because our production is longer than one symbol here. And then, well, we can add code. If symbol equals to our non-terminal symbol A, then we read another symbol. If there's not a non-terminal symbol A, well, it doesn't match, so we just complain about our input here. And after we've read this non-terminal symbol A, we try to read the next symbol here, and this needs to be a C. So if our symbol equals to our character C, then we can read the next character again. If there's no C but another character, it's not part of our grammar, so we complain again here. So that would be the first rule here. And the second rule is a bit simpler because we only have to match the single B. So else, if our symbol equals to our single B, then we can read the next symbol. If there's no B, then finally, it doesn't match any of our rules. So the first gray box here implements our first rule, and the second gray box here implements our second rule. Now, wait a bit. What's with this capital A? This is not a variable we've declared. This is nothing we've declared, actually. So we need to ask, can this work this way? And, well, the obvious answer is no. Your compiler would obviously complain because, well, your compiler doesn't know anything about this uppercase A, which we intend to be a non-terminal symbol. So we need to do something else. And here is where this recursiveness of our recursive decent parsers comes in again. Because we have a recursive definition, so we use our non-terminal symbol again in the production for A. So we have A as non-terminal symbol on the right-hand side as well as on the left-hand side. We now, because we can go through this as many times as we want, we now also need to recurse in our code to enable that we can go down this rabbit hole as far as we want and can go back up again and don't lose any context. So we'll need to change our parser a little bit. So what we need to do is actually, for each of our non-terminal symbols, we need to write a function that recognizes this non-terminal symbol or complains about anything that's wrong. So whenever we encounter a non-terminal symbol such as A, we have to parse its production. So if we implement the parser as a function, that's easy to do. So let's say we have void A, so the function that's able to somehow parse our productions for A. And then we can start. If our symbol's a symbol that we read, so that now needs to be implemented somehow already as a global variable that calls this next function before we call A. So if our symbol equals our character A here, then we know, okay, we can continue. We're on the right way. Then we can read our next symbol here. Now we don't check for the next symbol because it's a non-terminal symbol. So what we have to do is we need to go down to A again. So we need to call it recursively and then maybe check again if there's an A. And that's exactly what we're doing. So A here recursively calls itself. So if we have an A and maybe another A, because we went down this production once, then, well, we come into this function again and we read another A. And maybe there's another A or not. If there's no other A, well, there needs to be something else. Let's take a look at this first. So what is this something else? Well, if there's no A, it must be a B here. So this again is our else pass. This is unmodified. So if our symbol at the beginning is not another A, we check if it's a B. If it's not a B, well, then we complain about it. And finally, when we return from all of the calls to A we've recursively done, we're back up again at the same level here. So we match this A to the same C as the same level of the rule. And then we check, after we've gone through so many recursions of A as is required, we check if after this a C is coming up. And you see if you call A recursive again, maybe 3 times you go through A, read an A, go here again, read another A, go here again, read another A. Then, well, finally you read a B in between, and then you come up once here again, you need to read a C, come up to that level once more, read another C, and finally read the final C, and you've just resolved your string here. So some more implementation hints, not in C, but in an easily understandable language, can be found in Word's book on writing recursive decent compilers. And that's a technique that was already known in the 1960s and very much used in the 1970s. And this also defined what these languages wanted to express. Now, if your language gets very complex, of course, writing such a recursive decent parser from hand takes a lot of time, especially you can make many errors just by getting the recursion wrong, stuff like that. So maybe there should be other ways to approach this problem. But first here, what is important to learn from this slide, if we have some recursion, on the right hand side just calling our, whatever non-terminal symbol again, or another non-terminal symbol, we have to call this function again to try to derive something from this non-terminal symbol. If we had more productions like a capital B here, and we would go have a capital B somewhere, so a non-terminal symbol B, we just recursively call the function that implements parsing B. So this allows us to count, so that's what regular expressions didn't do or couldn't do. So by recursively calling the parser, our computer using stack frames that are added to the bottom of our stack again and then deleted whenever we return from this function here. This enables us to count and to ensure that we can match this A to this C in the right recursion of our production.